Hey, thanks everybody for coming, and thanks very much to Ciarán for agreeing to come and speak to us. So, Ciarán's going to tell us about nonlinear dynamics of frustrated magnets. So, over to you, Ciarán.
Thanks, Shane. Yeah, thanks a lot. So this is, I've tried to make this kind of hopefully general and understandable. So now that not everyone's here is an expert or kind of working on condensed matter. So the most important thing, hopefully, is that you get some sort of takeaway from it. So please do ask me questions. I'm going to kind of go through it slowly. I have a lot of slides because I have some later results from our own work, but it's not really so important that I get there. Again, the most important thing, hopefully, is that you take away something from the talk, even if it's just something small, okay? And so please do interrupt me and ask questions if anything is not clear. Okay, and and then I just want to, this works good. I just want to say that a lot of the work that if we do get there, that I'll show later, is in collaboration with collaborators at the University of Cologne, where I was previously before joining UCD, Yoshido, who did a lot of the hard work, and Simon Trebst, and then the University of Toronto, Emily Zhang, and okay, so let's think about, so I'm studying quantum many-body systems. So let's imagine that you have a quantum many-body system, okay? And so I will typically talk about magnets as a particular example, but you could think about your favorite many-body system, your favorite quantum many-body system, okay? And you'd like to learn something about it, right? So there's different perspectives you could take. You could look at static properties of the system, okay? So this would be encoded in these static correlation functions. Okay, so this is some operator, I and j at two different sites in a lattice. I can think of a lattice system. And I take the expectation value, okay? And so an example of this for magnets, a very popular example, would be something like this static structure factor, which is just this operator where I have spins, okay? So say SCSC or SXSX, that tells me about the static magnetic order in the system, okay? And here's a kind of fancy theory example for particularly exotic kind of static magnetic order. Okay, so that's one side. And the other side, I could look at dynamics of the system, okay? And I'm going to talk about just dynamics in equilibrium, so there's no non-equilibrium craziness going on here. I'm talking about thinking about the dynamics or the excitations of my system, okay? And so this would be encoded, again, in time-dependent correlation functions, okay? It's going to have two different operators, and now there's a difference between them, okay? And so on the left, I'm looking at static properties or properties of the ground state. And on the right, I'm looking at these dynamics or the excitations of the system, okay? And again, a popular example for magnets, which is what I work on a lot, would be, say, the dynamical structure factor, okay? And so this is, again, just if I put in spins here, say SCSC, this would be the dynamics of the magnetization dynamics or the excitation of the system. And here's an experimental example for a very famous square lattice antiferromagnet. Okay, so obviously these two perspectives are not independent of each other. There's an intimate relationship between the static properties, the properties of the ground state, and the dynamics or the excitation of the system, okay? So for example, if there's a excitation gap in the spectrum, then that implies that the static correlation functions decay exponentially, okay? So they're not independent of each other, but learning about one can tell you about the other, and vice versa, okay? And so all of these kind of things here that I've written can all be encapsulated in an overarching framework that will be referred to as linear response, okay? These kinds of correlation functions. Okay, so what is linear response? Again, you take your favorite quantum many-body system. In my case, I'll think about, some magnet, okay? And you add a perturbation to your Hamiltonian. And in this case, the perturbation for a magnetic system, the most natural one is a magnetic field, okay? So a magnetic field couples to the spins. These are the spin operators. So it couples to the spins of your system. And here, the magnetic field could in principle be, it could have an index I, so it could depend on its location in space. And then it has a time dependence too, because it could depend on time, okay? So here I've drawn kind of sketch of a pulse, let's say. Okay, so you take your quantum many-body system, you perturb it a little bit, in this case with a magnetic field, and then that generates some magnetization in the system, or induces some magnetization in the system. And you could, because it's a perturbation, you could expand that induced magnetization in a power series and powers of this perturbation, powers of the magnetic field, okay? So there'll be a term that's linear in the magnetic field that you've applied. There'll be a term that's quadratic, cubic, et cetera, okay? Right, and if you if you neglect higher orders, so we're just looking at the linear part, so that's the part that's proportional to the perturbation. How I often think about it is if you have a many-body system and you poke it a little bit, then a linear response, the response of the system is proportional to the magnitude of your poking. Okay, So here in the linear response, it's encoded in this function, chi1, where there's linear susceptibility, and it's exactly this kind of two-operator time-dependent correlation function, okay? Just like we had before, okay? So by adding this perturbation, at the lowest order, you capture exactly this kind of correlation function that we were just talking about. Okay, and a super simple example of this, let's take the simplest magnetic field, time-dependent field. So we're taking a uniform magnetic field, and it's just a delta function pulse at the origin, okay? So I have zero field, then at time zero, I have a pulse, I have some strength, P0, and then I have zero field again, okay? So it's just a, real sharp impulse to the system. And then at some later time t, I look at the magnetization of the system, I measure it, and I look at the induced magnetization, and then I can expand it, like I said, in this power series, in this P0.
So in your last response, you have the imaginary part of this?
Yes, I did, yes.
No view for how to review the transform or something?
So it depends. So so this correlation function, S alpha, S beta, at 2 different times, will have some real and imaginary parts.
It should be real in the system you set up.
Real.
I think you're
Yes.
imagining that you're putting in a complex B.
No, so in the right. So maybe it's more clear in the next slide. Okay. So here I'm finding chi as a function of t. Okay. So this R1 of t, I can write the complex conjugate of R1 of t is the same thing, just flipped, right? So this is m of t here, m of 0, okay? The complex conjugate of this would be m of 0, m of t, but I just flip these two.
Isn't m real?
Yes, m is real, yeah. So I'm just saying that okay, so if you take this and I took the complex conjugate, I would flip these two, so I'd get m0, m of t.
Why isn't it real? Why is that?
It's real.
Because it's time dependent, right?
The complex conjugate is going to do nothing to it.
It will flip the order of the operators.
That you
Yes, so m of t, m of t has an e, if I write it in the, if I write it the time dependence, I have e to the minus I h2.
So you're fully transform.
That's what you're doing.
You're really talking the real math.
That's a real object. There's no question about that.
Expectation.
But the expectation value.
It's real.
It's a non-permission.
No, so
It's
it's,
real number. The complex conjugate.
so the complex conjugate, so this is m and
Complex
t.
conjugate is absolutely nothing to that.
It flips this.
No, it doesn't.
It does, that's how it's the complex conjugate.
Sorry, it doesn't.
You flip the order. If you think about it like the time, and it's that's how you flip the game.
M is a real magnetic field, surely.
Yes, so B is a real magnetic field. Right, so
I'm confused.
okay, so let's see what's the best way to
You're doing something else, which is
You can
not.
take the expectation value of the complex conjugate of m times n.
So the real formula is that it's m of t, m of 0, plus m of 0, m of t. Okay?
So is m an operator or a number?
M is an operator, yeah, M is the
I thought
operator.
it was a magnetization.
Yes, M is the total magnetization.
Is that not just a real vector?
So later on, it's maybe more clear when I have 3 operators or 4 operators, but I have multiple times.
Sorry, Ciarán, can I just check this?
Yeah.
Alpha is like X, Y, Z.
Alpha is X, Y, Z, yeah.
Beta is X, Y, Z.
Yes, so these don't have to do the same. So for example, this could be mx at t and y at 0, or I can flip, yeah.
And then the thing inside the expectation value is a non-permission operator.
Well, I don't know if you call it not,
Well, it's Hermitian. That's the Hermitian conjugate would flip. Yes. Both of those are Hermitian objects.
That's why it seems to me that it's a potentially complex number, because if you
yes, it is a, yes, it is a,
mx,
yes,
mx,
yes, it is a
my,
potential complex.
then its Hermitian conjugate was my mx,
Yes.
which is not equal to mx my.
Yes,
So this is potentially complex.
yes, exactly, yes, yeah. And it's evaluated at different times. 2 operators are not evaluated at the same time. Okay, so the way you derive this formula is very simple. Okay, so you start from your Hamiltonian, you shift it like this. Okay, then you want your wave functions in the interaction representation, where this is your treated your interaction. So then you can formally solve the Schrödinger equation. So you get psi of t as some time ordered exponential of e to the I, this term b of t times s, acting on your wave function. And then you do the same thing for the Ket version of it. and you take the expectation value of m, so this part here, and then you expand out these time-ordered exponentials on both sides, and so you get this power series. If you're expanding out, you know, the exponentials happens p's, okay? So expand it out, and it's kind of linear, you get two contributions, one that's like m of t, m of 0, and then the other one that's the time reversed, m of 0, m of t. Then you can combine them together to get a real and imaginary part. I mean, basically in this case, you would just get the imaginary part. It's, you know, if you think of the fluctuation dissipation theorem, right, this dynamic structure factor is related to the imaginary part of this operator, right? And the real part is the other part, right, the other component. So. That's really, I'm not doing anything crazy here. It's kind of, I mean, I'm just, you know, you expand out. Again, you formally solve this, the Schrodinger equation, expand out in powers of b, rearrange, and then you'll get, yeah, the imaginary part appearing here, which again, you can relate to the fluctuation dissipation theorem, the structure factor, and then there's also a real part to it. Okay, so here, as a function of time, this will be real, right? So chi1 will be real. And if you do it, say, for a simple phase, like the ferromagnetic Ising phase, so ferromagnetic Ising phase is basically just a ferromagnet where all the spins are aligned, pointing in the same direction. If you calculate, this is what it looks like in the time domain. If you look at it in the frequency, so here I've plotted, so obviously when you Fourier transform, there's a real imaginary part, you'll plot an imaginary part. And this peak here is just a spin flip, okay? So this intensity here is just associated with the excitation. So all the spins are aligned, you just flip a spin from up to down. And then this is this excitation here. And you can't really see it, but there's a tiny bump here as well, which is to do with flipping two spins, okay? It's just much smaller intensity, okay? And so in this linear response, you know, this chi1 in the time domain or frequency domain tells you about the excitations of the system. Does that make sense to people? People still hung up on the real imaginary parts?
Yes. Again, especially in the Ising case.
So here I've taken, this is chi xx.
The observables commute. You're saying they don't commute at different times, is that what you're saying? Or?
So chi x, so this is at chi xx. So I put an xx here. This is mx.
So that's it.
And this is the time domain. And then I take a Fourier transform. So chi xx of t is real, right? This is a real quantity. Right? And then I Fourier transform it, and here I plotted the imaginary part of xx.
You have the imaginary part in the Fourier transform, no problem.
Yes. And chi xx is also real, right? This is, I can find it, this is the real quantity.
The imaginary part of R1 in the Ising case, I have difficulty with.
So what is the difficulty?
I have two things that should commute in the Ising case. So what's forcing them not to commute?
So I mean, so these are the so basically, you know, you have all the spins are aligned, right? So mx here, you can expand it. Mx is s plus and s minus. And so you have an s plus and s minus. So then there'll be a term that's like s plus s minus, acting on the ground state. And that matrix element basically gives you then, I mean, another way of writing this is if I, you know, write this as either minus AHT, either AHT, and then insert resolution of the identity, then I'll get matrix elements times some exponential factors. The exponential factors I can write as cosine, but the real part plus I times sine. And so then I'll get matrix elements times cosine, the real part. I'll get matrix elements times sine, you know, which would be the imaginary part. And then I take the sine version of this. So the imaginary part, this is like sine of omega, you know, sine of e of t, e times t times this matrix element right at the time times the time. That makes sense. I mean, I haven't put all the details here, but basically, you know, if you just want to think about it, you write this as either the IHT and alpha, either minus IHT, you get rid of all the times, right? Either IHT acting on a Hamiltonian gives you an e to the I, you know, energy of that state, in this case the grand state t, right? And so then you get a matrix element times an exponential, an energy factor. The exponential e to the I, you know, e times t, you write as cosine et plus I times sine et. Okay, the real part is the cosine part, the imaginary part is the sine part. So then you get the imaginary part, you take the sine part. Okay? So maybe that's, yeah, so that's maybe the easiest way of seeing that. This has a real and imaginary part. There's a cosine omega t and a sine omega t, and that's how you. Is that
My confusion with that, I thought magnetization was a vector, but I think these ends are remission matrices, aren't they?
Yeah, so these are operators, so this should have
They're operating, so they're not magnetization that comes into matrix equations.
No, sorry,
That was my confusion.
yeah, sorry. So the operators, so they should be
It's a remission operator.
Yeah, exactly. Yeah. Sorry. Yeah.
So that was my confusion.
Okay, I'm sorry. Okay, sorry. I should have been more clear. Yeah, sorry about that. Yeah. I mean, these are the quantum mechanical operators that are. Sorry about that. Okay. Yeah. Okay, now I see your confusion about the. Okay. Yeah. Yeah. Sorry. Okay, so the operators and the arguments. Sorry. Yeah. Okay. Yes. And is that also?
No, I think we should.
Okay. Yeah, I didn't put hats. Right? That's probably confusing. Okay, so this is what a linear response looks like. You know, it tells you about the excitation of the system. In this case, it's a very simple excitation. Okay. And so, so this is super powerful. It tells us a lot about systems. A lot of our textbook physics is encoded in this kind of linear response. And so I want to stay on dynamics here, but I want to look at not these kind of correlation functions, but these higher order dynamical correlation functions. Okay. That if say 3 operators, 4 operators, and multiple times, okay? And so these kinds of things are not captured by linear response, and so we have to go beyond to nonlinear response, okay? And so okay, 2 questions then that naturally arise is why do this, right? So what actually information that's new could you learn? What's the point in doing it? And then also, just as importantly, how, okay? So even if there is important information that's new, how would you actually measure it? Right? How would you actually extract it from a physical system? So fortunately, there's actually a super already known way of doing this, super well-known way of doing this. So I'm going to answer this question first, and we'll go back to why. So how do you measure it? So it's quite straightforward. It's just a little bit of a modification of the setup I just had for linear response. So instead of having a single magnetic field pulse, we have 2 of them. Okay, so one centered at 0 and one after time delay tau. So the magnetic field, again, I'm going to write as a uniform field with just 2 delta function pulses. Okay, and t is the time delay between the second pulse and when I measure the magnetization. So now I can expand the magnetization again in a power series. And I've suppressed all of the time arguments and alphas and betas just to make it easier to write. So there'll be some part that's linear in both of the fields, some then quadratic parts, etc. So then I can do the experiment a second time where I only have 1 pulse. Okay, so let's say I do this with only the 0 pulse, then I'll get again, I can expand it in the power series. Then I do the experiment a third time, where I have both pulses, sorry, when I only have the second pulse, and I can again expand it in this series like this, okay? And so now what I want to do is I have these 3 different sets of data, you know, for these 3 different setups. And so now I take this combination, I subtract off the 1 pulse contributions from the 2 pulse contribution, okay? So you can see that a lot of terms cancel, and I isolate as the lowest order term this chi2, this mixed second order part. Okay, and I'll also get chi3s, again, 2 different mixed kind of ones. Okay, so the kind of key of this thing is that by engineering this 2 pulse scenario, we can cancel off this linear response part. Okay, and that's, you know, and why do we want to do that? Well, linear response, the reason it's so powerful and useful is because it dominates the signals. Okay, that's the lowest order and most dominant contribution. So if we want to see beyond it, we have to get rid of it somehow, okay? And so this subtraction procedure allows us to eliminate it from the signal, and then the lowest order signal is just this higher order responses, okay? And so it's the kind of like key kind of, you know, ingredient for this kind of technique. So that we access these chi2s and chi3s, and so as I kind of, you know, advertise these, so this is, they have arguments, they have time arguments, and they have all sorts of indices, okay? And as I mentioned, these are related to higher order dynamical correlation functions, okay? So for example, this chi2 is now the real part. So again, if I expand it out the exponential, this would be the cosine part of these two correlation functions. So there's 2 different ones, because now I have different ways of ordering the times. It hits 0, t plus tau, and here's 0, tau, t plus pi. So these are different time orderings. So this actually makes a difference to the matrix elements. And then chi3, there's again, I won't go through it, but there's also complicated formulas for chi3s. And here there's some, again, some linear combination of these different correlation functions. and here's the imaginary parts, okay? So they're quite complicated, so I'm not going to go through any of them, but I just want to highlight that you get some linear combination of the possible dynamical correlation functions. Yeah, and interesting to note is, obviously there's a lot of information that you're missing because there's 4 different, say, functions here. You're only getting one particular linear combination. Actually, it's kind of known that you can use, basically use non-classical light, you might be able to access actually a different kind of linear combinations. Okay, so now this kind of perspective switch from linear response to nonlinear response, or from these 2 operator correlation functions to the higher order ones, also necessitates a little bit of a switch in how we view these things. Okay, so beforehand we would have had something like, I would have plotted frequency on the x-axis and the intensity on the y-axis. We might have had peaks like we saw for the Eisen case that tell us about excitations of the system. For these cases, I have 2 times, so then I'll get 2 frequencies. So I'll actually get a different kind of plot of 2 frequency axes here, okay? And then these peaks, obviously they'll be then in the, you can't really see the line, but yeah, so these are now spread out, in this case, across the diagonal, okay? So obviously, this is a sketch. I mean, this is really a 3D plot, right? So there'll be 2 frequency axes, and intensity will be color on this plot, okay? So we have to, the way that we plot these kind of things is a little bit different, okay?
So I didn't quite understand what you're showing us here.
Okay, sorry. Sorry.
There's supposed to be 2 plots superimposed on the left there, is that what it is?
No, sorry. Okay, sorry. Yeah. So on the right here, so this is kind of just a cartoon of
This is still linear response.
Yeah, exactly. Yeah. So this is what kind of is a cartoon of this kind of situation. I'm plotting on the y-axis the intensity. So in this case, the Fourier transform con.
Yes.
And on the x-axis, I'm plotting the frequency. And so then the intensity is, I have some plot like this. And then in the, so then I do a sketch of that where I had not just 1 peak, but I had several peaks. So I had, again, I had on the linear response on the left-hand side, I had frequency on the x-axis. The imaginary part of this response function.
And the 7 peaks are due to the fact that
in this particular case, I've kind of just drew a sketch, but here there's maybe 4 different kind of excitations in the system. So this is not meant to be the Eisen case, sorry. Yeah. So this is just some sketch of some other kind of scenario that in this case has 4 different types of excitations. And then, right, but then when I do this, when I have 2 times, I get 2 frequencies. And so then I have both 2 frequency axes as opposed to a single frequency axis. And so now these things become, spread out in this 2-dimensional frequency space. I mean, I'll show plots later, but these are really actually points, right? So you get 2 frequency axes, and if you drew a 3D plot, the intensity would then be, this 3rd dimension. Okay.
Yes.
Later I'll show color plots. I won't show 3D plots because they're kind of complicated to actually interpret. So here there's 2 frequency axes, and there's a 2-dimensional frequency plane as opposed to the 1-dimensional frequency plane for the linear response. Does that sound?
Yeah, no, it's a 3-dimensional plot. You're just showing us the.
Yeah, and kind of project, like a top-down kind of view. Okay, and so this particular technique that I've just described to you, it has a name. It's called, so in general, it's called 2-dimensional coherent spectroscopy. So 2DCS for short. And the particular version that I will be, mostly talking about today is the terahertz version. And so this was 2-dimensional coherent spectroscopy, 2-dimensional because it's 2 frequency axes, like I just described. And it's actually, goes back to the 70s. So there's an NMR version of this, and from the 70s, and then there's an optical version of this in the 80s and 90s. So optical nonlinear response is a huge field of physics. There's countless textbooks, conferences, papers on nonlinear optics. And nonlinear optics is also super important for many applications. And so this is a very well-developed field in the optical range, and also for NMR. And so let's say the newest thing in the last, say, 6 or 7 years is to expand the terahertz range of radiation. Okay, so instead of using optical pulses, they use terahertz pulses. Okay, and so terahertz pulses are nice because these are then within the energy range for magnets, and that's why this talk is about magnets. Okay, but it has other applications. I mean, before I go to magnets, so in the optical range, for example, it's used for chemistry. There's a nice example here where these are the 2 frequency axes. Here's some peaks. There's 2 different excitation modes along the diagonal. These 2 here, they're vibrational modes of this molecule. There's also these cross peaks here in green. And these cross peaks basically tell you that these two excitations are coupled to one another. And then as a function of time, these cross peaks disappear, which show you that these two vibrational modes are no longer coupled to one another. And that's actually because there's a bond that's broken as a function of time. So by monitoring these cross peaks as a function of time, you can actually monitor then when this bond breaks, basically. So it's useful in chemistry for these kinds of things. It's also used, for example, studying semiconductors and transition metal glycosides. They're interested in things like exciton physics. So these are kind of like particle hole-like excitations of the semiconductor. And these are some complicated, again, so it's very well used in chemistry, other fields of physics, even in the optical range. And so in magnets, this is a more recent development, only in 2017, because for magnets, you really need to push these terahertz frequencies, and this only became possible with like regular tabletop sources within the past decade or so. So the first experiments for a magnetic system was only done in 2017. And the setup is kind of like what I described. There's some sample, some material. They have some pulses A and B that are separated by a time delay, and then they measure the magnetization of the sample. And you get plots like this. So this is, so I won't go into detail into what this particular plot shows, but it has a two-dimensional frequency plot. Again, it's a color plot. You see there's different peaks. And here they're probing a particular excitation mode of this magnet.
So what was the obstacle technically to doing it to getting those high frequencies from?
Yeah, that's a great question. That's a good question. I actually don't really know the details of why. I'm not an expert on electromagnetic pulse generation. So my understanding is that for tabletop sources, I think a lot of these are like generated by like oscillator antenna kind of like sources. And so I think that just being able to fabricate sources that could create frequencies or wavelengths in this range was, I guess, very challenging until recently. But I don't really know the details, to be honest. So even now, it's still challenging. It's not like this is an easy experiment to do. But you can commercially buy terahertz sources now. So if you set up a lab, you can commercially buy such a source. Okay, so there's a two-dimensional plot here that has all sorts of different peaks. And if you, again, I won't go into detail, but if you can separate this out in these different components, chi2, different chi3s, and they're given, okay, so the contrast and projections, they're given different names, the peaks are given different names, and the names are borrowed from the optics literature. Again, it's not so crucial for this case. Okay, so there's some information that you can get about the excitation. Okay, so these kind of experiments kickstarted a lot of theoretical interest. So all of these are theory papers. There's not a lot of experimental papers because the experiments are actually incredibly challenging. The reason for that is because you're doing the subtraction procedure where you have this very strong linear part. So this very dominant term, and then you're subtracting out huge numbers to look at some very small numbers, this nonlinear part. Okay, and so if your signal to noise is not very good, then the signal you get can be sometimes below actually your noise. And so that's what can often happen, that they'll do the subtraction and they basically just get noise. And so the signal is just too small compared to the noise that they have. So this is kind of, so there's not a lot of experiments watching yet because it's really challenging to actually get these very small nonlinear signals above the noise. But that hasn't stopped Paris from writing all sorts of papers and coming up with all sorts of interesting things that you could potentially one day look at. So then that brings us to why. So why was there so much interest in it? What new information can we learn? There's a lot of different things that you could potentially learn. And this is also not an answered question yet. But this first experiments were in 2017. The first kind of theory papers were in 2019. This is a relatively recent kind of field. So there is no concrete answer yet to this question, maybe completely. There's lots of different proposals, but it's kind of ongoing work to see actually why this is interesting and what new things we could learn. Right, so what new information can you learn? Nonlinear response in general, I'll talk about magnets, but in general, it's becoming increasingly popular actually in recent years, not just in magnets, but even in electronic systems. So for example, in electronic systems, it can be used as a probe for the symmetries are broken or not. So chi-E, here means the electric field. So this is not now looking at magnetic fields and the magnetizations, but it's looking at electric fields and electric polarizations. This second order chi2 is actually only 0. it is 0 if there's a certain symmetry of the system, okay? And so here there's a plot of this chi2, the temperature. You can see that above a certain temperature it's 0, and below this temperature it becomes finite. Okay, so then that means that at this transition, it must be that the symmetry is broken, because only if the symmetry is broken can this thing be non-zero. So this tells you that there's a finite temperature phase transition here, where the symmetry becomes, the symmetry is broken. So this is quite an important piece of information, because for this particular material, which is one of the high temperature superconductors, it was extremely actually challenging to see this particular symmetry breaking in any other kind of probe. So it's only found via this kind of what's called second harmonic generation. And so it's a really sensitive probe for breaking certain symmetries, which can be very useful.
So what system? What type of system was it?
So it's one of the high temperature superconductors.
Okay.
In the basically doped high temperature superconductor. And this is basically, I don't know how much you know about high temperature superconductors, but there's like this famous pseudogap phase, and this is basically the pseudogap TC. This is from Tim Shea's group at Caltech. And then the other thing, again, this is more solid state thing, but it can also be used to probe the topology of band structures in a kind of complex way.
So this is your order parameter on the. I can't quite read the.
Oh, sorry. You mean this thing?
Yeah, the vertical side. The vertical is your order parameter.
Oh yeah. So here, well, okay, we're just normalized intensities. But essentially, this the points here, I omega is a current actually. So it's a current that
the blue one is,
and this is a current at twice double the frequency. So this is basically the blue part is basically the nonlinear contribution to the current, and the red part is basically the linear contribution to the current. So this is basically the blue part is basically a measure of the chi2, the nonlinear susceptibility, and the red part is basically the linear one. So you can think of it as a proxy for the order parameter.
Is this showing like a second order crossover transition?
So this would, so I mean this right, so this looks like a second order phase transition. I mean, so I've only showed you one particular piece of information, so I haven't shown you any thermodynamic data for this particular transition. So it's a little bit, I'd say it's a little bit complex. It's quite a mysterious transition, a finite temperature phase transition, which is not really well understood. So it indicates there's probably potentially a second order phase transition, but it's but obviously this is not thermodynamics. This is and it's also a proxy for an order parameter. But yeah, it's likely there's a second order phase transition.
Could you tell the difference between second order and crossover?
Yeah, in a crossover, I mean, so in a in a crossover, let's say if there's a crossover, there's no symmetry breaking. That means that invergent symmetry, if invergent symmetry is always broken, then you should always have a finite chi2. And if there's always a finite chi2, then even at high temperatures, you should observe a finite chi2. And here, okay, obviously they have some experimental error bars, but they don't observe a finite chi2 above this temperature. So there's really a sharp, I mean, there's really, obviously there's experimental noise, but there's a relatively sharp transition from 0 to a finite value of this thing. Okay. And then here, so here there's nonlinear Hall. You might have heard of the Hall effect or the quantum Hall effects. There's also nonlinear versions of these things, and the nonlinear Hall effect can tell you about certain properties of the band structure in a similar way that the conventional Hall effect can also tell you about some properties of the band structure of the material. And this can tell you about a slightly more complex probe of the band structure. So this is for electronic systems. So it's, like I said, become very popular. But I want to talk a little bit about magnets. Okay, so for magnets, and in general, linear response, very powerful framework to understand a huge range of different phases in the phenomena. But it's not perfect. Okay, so sometimes it does not capture all of the key physics. Which is not, it's not guaranteed. That just because you do a linear response, you're going to capture every single thing you want to know about a particular phase. There's no reason for that to be true. And so there's two particular examples I'll focus on in this talk, just related to kind of the work that I've done, and will hopefully be, at least the first one, straightforward to follow. So these are examples of things that you can get basically from doing the nonlinear response that you could not get from doing the linear response. Okay, and the first one is hidden or dark excitations. These are excitations that are basically just invisible in linear response for particular reasons I'll in a second. Okay. So it's first failure. In linear response, like I said, you're looking at correlation functions like this. So then if you look at matrix elements, the matrix elements you're looking at are matrix elements like this, okay? Here again, I've written, you know, e to the IHT, SI alpha, e to the minus IHT, and I'm just taking it as a matrix element. But this is the matrix element. I've inserted resolution of the identity here. And so P here are excited states, so then in the full expression I would be summing over. But they'll, you know, be composed of these matrix elements. So I start state from the ground state. I activate S minus on the ground state, and I get to an excited state, okay? So let's say that the magnetization was conserved along the Z direction, okay? That means that if I start in this state, it has some value of mz. If I do S minus, then I'll get a state that has mz minus 1. Then I'll do S plus, I'll get back to mz, and I'll get back to the ground state, okay? So these particular excited states that I'll access have a delta mz away from the ground state of 1, okay? So this is just a kind of selection rule. We typically refer to it as a dipolar selection rule, okay? Right, and so it's basically saying that if you have some, you know, state that has a particular quantum number, that quantum number is conserved, this operator reduces that quantum number by 1, and so then the excited state that you can access here differ in a quantum number from the ground state by 1, okay? And I can put an S plus or S minus here, so it's, that's what this absolute value is, okay, right? So now you're not actually accessing all of the excitations in your response. You're only accessing a particular subset of excitations, okay? Those that differ from the ground state by 1 from this quantum number, okay? Now, say I could put in other quantum numbers or other operators here, and in general, you know, as long as the quantum number is conserved, the same thing will be true, okay? In the linear response, you'll only access a certain subset of the excitations, those that are, you know, plus or minus 1 in quantum numbers away from the ground state, okay? So you only really get access to a restricted part of the excitation spectrum. Okay, what about nonlinear third order response? This has 4 operators in it, okay, in principle at different times. So this has matrix elements that look like this. It's a P, Q, and R are excited states of the system. And so now I can have, say, 2 S minuses. So I go from mz minus 1 and minus 2. And so now here I access excitations that are 2 away from the ground state, okay? It's a little bit better. So I have a little bit more access to some additional excitations. So these are given the name quadrupolar, okay? Quadrupolar excitations. So then I can access new excitations in this third order nonlinear response that I could not access in the linear response, okay? And they're completely invisible here or hidden, and here they become visible, okay? And obviously you could, if you wanted to say, go to 5th order and you get again even more. Okay, does that kind of make sense to people? Okay, and so then I'll just basically show a simple example of this actually in action, which is a spin 1 model. So there's the Heisenberg interaction, si.sj operators. And there's this term that's called usually single ion anisotropy, and it's like SC squared, okay? And both of these numbers are positive. And so if D is positive, then there's a minus sign here, so you want SC to be plus or minus 1, okay, to minimize the energy. And so there's actually 2 ground states. There's one for all of the spins are in the +1 state ferromagnetic. There's a second ground state in which all the spins are in the -1 state ferromagnetic, okay? There's 2 different ground states, and they're exact perfect diacritic states. They're all +1s or all -1s, okay?
So are you summing over alpha in your term here? You're not.
Oh, sorry, in this term here?
No, in the second one.
In this one here.
Oh,
Oh, sorry, and this is here.
Z, sorry.
Yeah, sorry, sorry. Yeah. So this is only along a single direction. So that's why this plus or minus 1 are polarized along Z. Yeah. So there's just 2 ground states, yeah. Okay, so then there's different excitations to the system. So there's this is weird. So there's a 1 magon excitation. So here the arrows mean a +1 state, and green means 0. And with spin 1, so you can have +1, 0, and -1 are the 3 states for spin 1. Okay. And so here you basically one of the +1s you've reduced it by 1 to a 0. So delta SC is 0, and delta MZ is delta SC is 1, and delta MZ is 1. You have 2 of these, so a 2 magon excitation, right? And then you can have what's called a single ion band state for historical reasons. So single ion band state. And so this is basically a full flip from the +1 state to the -1 state, okay? And so this is a delta MZ equals 2 excitation, okay? And what differs it from the 2 magon is this is on a single site you actually flip by 2, because the 2 magon is a composite excitation, okay? So in terms of the elementary excitations, you have this 1 magon state where you flip by 1, and this single ion band state where you flip by 2, okay? And this 2 magnet state is not an elementary excitation, it's a composite excitation of 2 magnets. Okay. And I've just written here the operators. So the S minus is what creates this one in this case. Q here is a quadrupolar operator, and it's like S plus, S minus. So the S minus is what brings you down by 2. Okay. So then I have these 2 different kinds of excitations. And so if I look at the energy spectrum, so this is the energy spectrum of the system as a function of this D, okay? And the colors here, the red indicates states that are basically like dipolar. I mean, basically the 1 magnon state here. And then this blue here color indicates that basically these 2 states here that have delta n equals 2. So these states here are the 2 magnon states. And this other state here is the state I'm calling the ion band state. Okay. So if I focus here at large D and I make a cut, there's 2 excitations I should see. This excitation here, which is flipping by 2, and this excitation here, which is flipping from +1 to 0. Okay. So these are the 2 excitations I should see. But if I do linear response at this cut here, so this is D equals 5, and I plot it, you see that I only see 1 peak, which is at this excitation, 1 magnon excitation here. And this excitation that's here is completely invisible. Okay. Hidden is maybe the wrong word, it just doesn't appear, okay? Because again, these selection rules for the matrix elements force it to be, vanish. So there is an excitation here, but it's not accessible to me, right? It's a part of the excitation function that I just don't see in the response, okay? And so obviously we would like to have access to these kinds of excitations, quite interesting excitations. And so how can you access them? Well, if you do the nonlinear response, you can get access to them, okay? So how do you see that? So there's a simple, we'll go through a simple little setup. So I mentioned that you have a pulse here, a second pulse, and you measure the magnetization. So let's look at this particular set of operators here. So this is one of the 4 different contributions. I'm just taking one of them. So at time 0, you have an mx twice. That's this term here. So at time 0, you get mx times mx. So if you're in, let's say, the +1 state, 2 mx's can bring you to the -1 state. Okay. So you go from +1 to -1, okay? And then the system evolves for some time tau. And so it will evolve with an energy or frequency. That's this omega of this single ion band state. So this is the energy of this +1 to -1 field. Then at time tau, I will act just a single operator, mx. So I'll go from the -1 state to the 0 state, okay? Because I'm only acting a single operator. And then the system will again evolve. This time with the frequency of the 1 magnon frequency because I'm in the system in the 0 state, okay? And then at time t plus tau, I measure the system and I go back to the answer. So I go from 0 to back to +1. So this whole sequence then gives me a peak in this 2-dimensional frequency plane that includes here this frequency of this single ion band state, okay? And so this frequency or this energy was inaccessible to a linear response. And now you can see that in this, slightly more complicated setup, you actually get access to this additional energy that was invisible to you beforehand. And so if you look at this, if you plot this then in this, this plot looks a bit washed out. If you plot this in this 2-dimensional frequency plane, you see that there's 3 peaks here. One of them is the peak I just talked about, this peak here. The 2 other ones come from different R, so they come from different contributions from this chi3. But these 3 different peaks are associated with the energy of this single ion band state, okay? And so that's very, okay, so that's very nice. So now you see it, whereas beforehand it was invisible. And there are these 2 other peaks here and here. These are just really, nothing to do with the spin 1 physics. I mean, if you did the same calculation for an analogous spin half model, which doesn't have this, +1 to -1 kind of quadrupolar excitation, you would see exactly these 2 peaks here as well. Okay, so these are like related to these dipolar excitations or 1 magnon excitations. Okay, and so these additional peaks here, are unique to the spin 1 case. They're unique to this being able to flip from +1 to 0 to -1. It's not possible for spin half, right? You can only go from +half to -1. Okay. And then I will maybe just. It's also possible, in these particular cases, we had to have a somewhat stringent condition that I needed to have the magnetization to be conserved, because otherwise this selection rules don't apply. But let's say that you had you broke this perfect conservation, so now you could mix both the because MZ is no longer conserved, even in linear response, you could see kind of these kinds of excitations, although they're not as well defined. So if you did linear response, and sorry, it's a little bit small here, you would see 2 peaks. This was the one that was invisible beforehand, but it has a very small intensity because it has a very small kind of dipolar part, because I only broke the symmetry a small amount. And then in this nonlinear response, there's certain frequencies, it's a bit more technical, that are proportional to basically tell you how much quadrupolar part is it in it, okay? So even in the case in which the symmetry is not perfectly preserved, there's also some information here. Okay, so I think in the interest of time, I will skip the other example completely.
Okay, we're not rushed.
No, okay. Maybe I'll go through at least the first part of it. So the other failure I mentioned was this, if you have a continuum of excitations, a featureless continuum, okay? So featureless, you basically don't get any information, okay? So linear response is already kind of not telling you much, so could you learn more from nonlinear response? And that's actually one of the things, and so first I'll show you a schematic, and then I'll show you an actual real model. So for example, here's a scenario in which, so this is a linear response, I have a very broad peak here, which is just a single very broad peak. And here I have many small peaks, I should have probably drawn more of them, that combined together create a large peak, okay? So in this case, in both cases, if I saw a linear response, I would just see a very broad peak. But in this case, the broad peak is just a single broad peak. Here it's actually just many sharp peaks, but just superimposed together. That when you add them all up, they create overall a big broad peak. Does that kind of make sense? Okay, so how would I tell them apart? So here we're again we have access to 2 frequency axes here, okay? So now these excitations, again in a schematic way, get drawn out like this, okay? So along this diagonal direction, I would see this broadness, okay? So in kind of chemistry, this is called inhomogeneous broadening, so it's broadening along this direction. However, along the anti-diagonal direction, if I cut here, I see this, again, in chemistry, what they call homogeneous broadening, but basically I see this actually intrinsic line width of these things, okay? So I actually see the fact that this is broad peak is actually, broad only along one direction, which is the direction I can see in linear response. But when I have access to the 2-dimensional plane, I see that along the other direction, it's actually very sharp. So I can see that then that this is composed of many sharp excitations. Okay, so this is kind of a schematic thing. There's a real model for this happens, which is the 1D transfer model. And this paper in 2019 is actually what the kind of theory paper that kickstarted a lot of the real interest in the system and this technique. So in the 1D transfer model, in the ferromagnetic phase, it's a ferromagnet, so all the spins are pointing up. And then here you've basically made a single spin flip, so you flip one of the ups to down. And that creates a domain wall, they call it. Okay, so these little dots here represent domain walls. So basically here it's a domain wall because this is all up, this is down. So at this bottom, which you go from up to down, this is called a domain wall, okay? And here there's 2 of them, okay? And then K minus K indicates that when you flip a single spin, you can create these 2 domain walls, and in 1D they're free to move, and they'll move with equal and opposite momentum, okay? So one of them will move momentum K, and one of them will move momentum minus K. So then you actually get by just flipping a single spin, you actually get a whole continuum of excitations. Because K is some continuous variable, right? It's the momentum, so it's a continuous variable. So you get a continuous spectrum. So if we look at the linear response, in the time domain, it's actually very hard to see anything. It's super sharp decay and very small wiggles that are hard to see. Then if you look at that in the frequency domain, you get this very broad peak, okay? Which is domain wall, so DW is domain wall continuum. The term spin-on is also used, but I think domain wall is probably easier in this context. So domain wall continuum. And again, it's not actually, a broad peak. It's actually just many sharp peaks. Just there's like the basic delta function peaks, but I have a continuous, they vary over a continuous parameter, K. So then if I sum a lot of delta functions together, it's like one big broad peak. And what about the nonlinear response? So this is the nonlinear response in the time domain. So this is T and tau. The Fourier transform in frequency, like what I had before. Again, okay, the resolution is not great, but you can see that there's kind of a sharp line here. And this width of this thing is basically the width of this thing. Okay, so this is the broadening that I see in the linear response. But actually, like I said, this thing is not as thin. This is actually really made up of many sharp peaks that are delta functions, which I can't draw, but the delta functions. And so these have a very tiny width. And so I'm in 0 with really. And so then this, I can see that this is actually very sharp on this direction. Okay. So in the linear response, I just see a big featureless blob. But in the nonlinear response, I actually see this very sharp anti-diagonal direction, which tells me that actually this featureless blob is actually made up of super sharp long-lived excitations.
So is this an analytic treatment?
This is, yes, this is analytical because the 1D transfer model can actually be exactly solved. And so then you can also calculate these nonlinear response functions. Yeah, so this is all exactly solvable. And so that's why these are actually, this width is actually not finite. It's actually, this is really the infinite lifetime because it's an integrable model. And so actually this is like a delta function. These are like, it's really as sharp as possible.
But presumably they're finite with, if you choose a finite chain of transversalizing.
Actually, so the finiteness of the chain limits the momentum.
But just choose the finite.
Yeah.
It's easily solvable there.
Yeah. But so that all happened there is that you discretize the momentum space.
Yes.
And so then basically this thing, if you don't have a lot of this is really like superimposed many different peaks.
Yes.
But if you don't have a lot of K points, then actually what this will look like is not a big blob, but you'll just see like 10 or 12 sharp peaks.
Sure.
And so then this thing here will basically, instead of looking like a line, will look more like a bunch of dots.
Yes.
Yeah.
Perfect.
And actually one of the things we did in our work is looking at finite size effects actually in this kind of thing. So we spent a lot of time thinking about what happens when you do it on a small chain. And then one of the interesting things about this that we kind of looked at, but I won't go into too much detail on, is if you start from this fermionic phase, you have these kind of free particles that have k minus k. And it's actually known, for a very long time, that if you add a longitudinal field, so this is another field, so the transfer Ising model has one field in one direction, and then you add another field in another direction, that you actually get a linearly confining potential between these free particles.
So you're adding in it.
Yes. So if I wrote down the Hamiltonian, there'd be like an SD, which would be like the Ising part.
Yes.
And then the transverse field would be like along X. And now I'm adding it in the field along Z. So along the same direction of the Ising. So it'd be like
Ising in the magnetic field made transverse.
Yeah, you could also think of it as starting from the other exactly. Yeah. So it's like you think of the classical Ising model with a Z field, and then you add a transverse field. And I mean, this is the opposite limit. I mean, here the HX is small compared to it. But anyway, and so this creates a linearly confining potential. And so this is analogies to people kind of were interested in studying it in like I think the early days because there's some analogies to confinement in more complex cage theories and things like that. And so then this continuum that was here actually gets split up into these sharp band states. And they're sometimes called mesonic band states, again, an analogy to confinement in quantum thermodynamics. So you get a bunch of very sharp band states, okay? And so then we were interested in looking at the nonlinear response. And again, I won't go into detail, and it's very hard to see actually in this projector. But if over here there was originally this very sharp line, and as you increase the confining potential, you see this discretization start to happen to these band states. And if you're over here, which is like 0.1, so it's a small kind of confining, small field, relatively large confining potential, you get this band state spectrum. And I won't go into detail, but if you were to zoom in here, you actually get a super complicated, very complex, very rich structure to this thing. Okay, so beforehand it was just a single line, basically just a single, very simple line. And now you get all sorts of peaks, you get all sorts of in between things. There's all sorts of labels here that I won't read. There's all sorts of different processes that contribute to these. So there's the case in which the pulse creates a domain wall, and then the second pulse breaks apart that domain wall. And there's also processes in which you can like join two domain walls, and there's all sorts of different complex processes that lead to all sorts of different complex features. So it's a super rich kind of thing. Definitely, we kind of started looking at this, but it'd be interesting to look at, things like the critical properties of the transfer Ising model, where it has this very fancy integrable E8 kind of field theory structure, and seeing how that looks here. And also you can think about things like string breaking, stuff like that is studied a lot in these 1D models, and see how it again manifests in these processes. Okay, but I won't go into too much detail, but just to tell you that even in a very simple model, your things can get very complex very fast.
Sorry, when you said E8, what did you mean by that?
Oh, sorry. Yes, this is kind of technical thing. I mean, if you one of the transitions here, if you tune to the transverse field isomodel phase transition,
Yes,
and then you add this longitudinal field,
yes.
then the critical theory there can be described by this EH, field theory. So EH is one of these Lie groups, exceptional Lie groups. And so basically, I think there's a famous paper by is it Zeldovich or from the 80s or something like that.
Yeah,
I think
that's Zeldovich.
yeah.
I think it might be Zeldovich and Zeldovich.
Yeah, I think it's maybe
It is that you meant.
I think it's maybe 82 or something like that.
Yeah, no, I know.
Yeah, so
Okay,
so that's been observed in materials. I mean, this even so that they're the band states, the band states at the EA point have a particular like golden ratio kind of spectrum of the mass. So the masses have like a very special ratio.
You required a complex magnetic field for that. So how did you add a complex magnetic field?
No, for that case, you just need to add a longitudinal field. You tune first to the critical point, and then you add a longitudinal field. I think is the.
But it needs to be complex.
Out
in the complex plane.
No, not for the physical system. And I don't know if the original calculation they used to make complex fields, but I mean, it's only obviously in the low energy limit that it looks like it's 58.
Do you have a reference for that?
Yes, I can definitely. Yeah, and then this other scenario where I said that you just have a peak, a broad peak, which is not composed of smaller peaks. Then when you do this, you put in this two-dimensional frequency space, it'll be very broad along both directions because it's just a broad peak. So there's both broadening along this direction, like a linear response, but also broadening along the anti-diagonal direction. So then you can easily tell it apart from this other scenario. Okay, and so then I don't know how much. I mean, there's another like sample, but I mean it would take another 5 minutes. So okay,
not half an hour is fine.
Yeah, yeah, no, probably like 5 minutes. Yeah.
Can I ask a question? So just in general, like if you wanted to see in your pictures if there's any kind of indicator of what the long time steady state might look like, is there some corner of your picture where that might be appearing? Like I just saw that like you had the transverse season model, and then you kind of broke the integrability where you might expect it to internalize in the long time limit.
Yeah, I mean here we're kind of looking at just equilibrium response functions in the grand state. So it's not really, I guess, thermalizing in that sense. I mean, we're kind of looking at
they're never in the higher parts of the spectrum.
Yeah, we're really looking at dynamical correlation functions, but taken in the grand state. So these kinds of correlation functions. So there is, I think, interesting things that we've not explored too much about. Hydrodynamic maybe observables at longer times. You might get short time dynamics that's dominated by these quasi-particles, and then hydrodynamic dynamics at longer times. So maybe that's could be something. I think there's one person working on something similar to that. But I'm not sure if it's not really a tool. I think well, maybe find a temperature you can think about thermalization. Maybe we can talk about it later. Okay, and the other example, so this was kind of a sketch kind of thing. There's other examples where you have a broad fictitious continuum. There's 2 different examples here. So what exactly they are is actually not so important. It's more just to tell you that these are 3 very different physical phases of matter. So one is a quantum phase of matter. It's called a spin liquid. It again has these fractionized excitations where you, if you flip a single spin, it creates 2 excitations that have equal opposite momentum. So again, you get a continuum. So here, this is the linear response, but here I've drawn it again as a color plot because I've drawn on the x-axis the momentum. So beforehand, we were always looking at 0 momentum. So I always just plotted intensity versus a frequency. Here, frequency on the y-axis, and on the x-axis, I put the momentum. So, and the stuff we're talking about, we only ever look at a single cut of this. So this is another interesting phase of matter that's completely classical. So it's a completely classical simulation. It shares many similarities to this. That's why they both have similar names. But this is a complete classical phase. So this was done with classical simulations. And then here is a magnetically ordered state, and that has a very large magnetic field cell. So maybe like 50 spins. So it's not like an anti-fermionic where it's just like up or down, but it's like 50 spins that have point in all sorts of directions, and that thing's repeated. It's a very large structure. And you see that all of them have pretty similar broad, featureless, washed out kind of excitation response. Okay, there's not a lot of structure. I mean, it's very broad and featureless. Of course, a wide range of energy. So then, could a nonlinear response tell them apart? Here I've just kind of zoomed into this plot and replaced this with a slightly different one. So the classical version of this and the quantum version of this look quite similar. The only thing that is actually very hard to tell is that here there's a gap. Actually, it's really hard to tell, but there's a little gap, actually excitation gap. And here there's no gap because it's a classical system. So that's really the only difference between these two in the linear response. So the nonlinear response, these have been calculated for this model. They have all sorts of crazy color schemes, so I'll just abstract it all that away.
So what is the color, the Kittai?
Okay, yeah. So I didn't want to, so basically it's the quantum phase of matter of a magnet. Kittai refers to a particular type of interaction. So it's a particular Hamiltonian with a particular type of interaction. So,
Which, I mean, it's a spin system?
It's a spin system, yeah, exactly. So everything's a spin system. It's a magnet with a particular type of spin interaction.
In 2 dimensions?
In 2 dimensions, exactly, yeah.
And what is the model?
So basically, it's typically defined on a honeycomb lattice.
Sorry?
On a honeycomb lattice.
It's the honeycomb lattice.
It's the honeycomb model, yeah.
Okay.
Oh, sorry, yeah, exactly.
Yeah.
It's that honeycomb model.
Yeah, it's a sigma X, sigma Y, sigma Z.
Exactly.
Okay.
Exactly.
All right, very good.
And so one is the quantum version, and the classical version is the same thing. Just you replace sigma X, quantum mechanical operator by a classical, spin. So you have Sx, Sy, and Sc is just vector. It's just a vector. It's a 3-component vector.
Okay, right.
As opposed to a quantum mechanical operator.
Yes. So the classical one won't have that decomposition into this the
exactly,
of the variables.
Yeah, exactly.
Is the vortex?
None of that exists. Yeah. So it's really just a classical vector, and it's really like an O3 model. But despite that, it has a very similar excitation spectrum, despite being completely classical. And this gap here is actually because in the quantum model there is this gauge theory-like description that gives you the gap, and there's no such thing in this. And so the nonlinear response looks similar. This is the second order to the third order. And so they have these line features, kind of like from before, but different in different areas. And the only thing to note is that near to the origin, there's actually no lines. So there's no stuff near the origin. That's because it has this very small gap. And this very small gap means that close to the origin, so close to the frequency, there's a little gap. So all of these things are shifted away from the origin. So these things are shifted. So what would you expect from the classical model? Well, for the classical model, I basically told you that in linear response, the only major difference is that one has a gap, one doesn't. So naively, we might expect, okay, maybe the only difference between these two is that one has a gap and one doesn't. So then here, I fill in this line here, and here, these things are offset by the gap, but I just collapse them in, okay? So for the classical model, this is what we might expect. Basically, this thing, but where I've got rid of the gap. And that's exactly actually what happens. If you do a classical simulation, this is what it looks like. We can remove the lines. And so it looks exactly like, this thing, just without the gaps, okay? So this has a gap, just like before, and this is no gap. So these two things, the quantum and classical version of this kind of exotic model, they actually share a very similar linear response, but they also share actually kind of a similar nonlinear response. They both have sharp line features. So you can't tell them apart. They're just kind of interesting that the purely classical physics can reproduce this very non-trivial quantum physics to do with gauge theories and fermions and stuff like that. Okay, these two, this is much easier. You choose, again, a complicated model that doesn't really matter, but it's a model that has a very large unit submagnetic order, so 50 sites. And they look super similar in linear response, but if you go to nonlinear response, they look completely different. Okay, so this is a very messed up spectrum because this is a very incoherent kind of excitation spectrum. And this is a very clean line features, okay? And so it's very easy to tell these apart. But these are very hard to tell apart, but these are super easy to tell apart. So then if I add this to my list, this has very different to these ones, okay? So I can at least tell apart some of these continua using the linear response, but not necessarily all of them. Okay, so now I will conclude, not too far of time. Okay, so going beyond linear response into this nonlinear response, nonlinear spectroscopy, I've given you kind of two examples where it could be useful. One is to access, I don't know how to use this word, but to access higher spin excitations, you refer to as multipolar excitations, which you can't access with linear response. So I had this example where this quadrupolar-like excitation. So these are hidden excitations in linear response that become visible when you go to nonlinear response. And the second case was helping to identify the nature of these underlying continua. In some cases, it maybe doesn't help, or it's maybe difficult to, this classical versus quantum Kitaev case somehow it actually wasn't very useful. But in other cases, like this Kitaev case, it's just large minority order state, it was actually useful. Okay. And these are just kind of two examples. Like I said, there's a lot of papers on this kind of thing. But hopefully I've given you a little bit of, if you take anything away, is that this kind of nonlinear response to these magnets, it's kind of a new tool. Okay, so it only become possible in the past couple of years experimentally. And it is a new kind of perspective. It's accessing new kinds of correlation functions, 3, 4 spin, more complex correlation functions, putting excitation within this 2D frequency plane. And so it can hopefully provide some new insights into not just magnets, but quantum many-body systems. I didn't talk about it, but it's also been used for superconductors. Also, it's being increasingly used for all sorts of different things. Also, people in semiconductors. So yeah, it's a new toolbox that we can use for quantum many-body systems, which will hopefully provide going forward a lot of new insights and interesting physics. So that's where I will leave it.
You mentioned about a limitation. I think you were specifically talking about the terahertz.
Yes, I was specifically talking about terahertz.
Is that you're subtracting the 2 first order contributions which are large and left over with
Right.
And then you were saying there's a lot of theory papers.
Yes.
If I was just wondering, do you have a sense of what the prospects are? Is this very, very hard to do? And do you really need very low noise levels to be able to see this?
Yeah, so that's a good question. I mean, I'm not up to date on the experimental. It is, so it has been it has been done. I mean, I did show experimental data, so it has been done on some magnets. Those magnets are super simple in the sense of they're very classical ordered states with very high spins, and so they're which gives kind of bigger signals. So as far as I know, there's been no study of a spin half magnet or a kind of quantum magnet. And for the prospects, I think a lot of people are working on it. So there's a lot of experimental groups that are very interested in it. And it might be a question of reducing the temperature. Also, these pulses also heat up the sample a little bit. The magnets that have been looked at, the experiments, they have like ordering temperatures that are like room temperature. They're like super well ordered. Whereas these more exotic magnets that be much lower ordering temperatures. And so there might be some things to do there. But a lot of people are trying very hard. And I hope that there's already been some kind of crazy developments in the experimental thing. And the way I described the experiment, you kind of sounded like you had to do these 3 different experiments, and you would have to do for each pulse delay. You would have to do it again. So you fix this tau, you win the measurement, you fix another thing. But now they can actually do the whole thing in like a single shot, through some very complex optics. And so that's only been developed in the last year or so. So there's a presentation by the experimentalists where you had like 2 different sets of data that look identical. It's like this took 3 days to do, and this took like an hour to do. And so it's really like crazy. So I think experimental, they're always come up with some ingenious new things. So hopefully there'll be some developments in that thing.
Is there any useful information in the equal time of the static the correlators?
Yeah, good question. Yeah. So that's slightly easier to access because that's slightly easier to access.
Yes,
and so that has been looked at for quite some time. So you can look at so basically, I mean, in that case, it would be the magnetic susceptibility. So you look at higher order contributions of the magnetic susceptibility. So there can be 2 reasons that can be useful. One is that again for symmetry reasons. Because again, certain symmetries can force the chi2, the magnetic part, to be 0. So whether or not that is 0 or non-zero can tell you something about the symmetries of the state. And then it's also been used, I think, in slightly more complex examples for superconductors. I'm not really an expert on that scenario, but I think that superconductors in a magnetic field can have quite complex kind of vortex arrays. And by looking at, so I don't really know the details, but by looking at the nonlinear contributions, you can learn some information about this kind of vortex. I think vortex dynamics in the state. So it has been used in magnetic susceptibility. And the other thing I think is that in very complex magnets where they have really complicated spins, so like if you have a very high, like one of the rare earths or something like that, where they have a very complex combination of atomic crystal fields and spin overcoupling. There again, by looking at the nonlinear magnetic susceptibility, you can learn some information about what is the in the same way that when you look at the magnetic susceptibility at high temperatures, you can get some information about kind of Curie laws and all this kind of thing. You can get some information about the effective moment of the system. By looking at the nonlinear thing, you can kind of learn a little bit more information about the structure of the magnetic moments. So there can also be information there. And because it's much easier to do, it's been looked at for many years.
Your Hickey liquid, the quantum one. Can you see the dynamics of those vortex modes?
Yeah, kind of. I mean, so these are calculations not done by us, but if I go back to here, so a little bit. So you can see this gap, which is kind of an indication of this vortices. So here, these vortices in this tab model are somewhat simple. They're kind of static in the exactly solvable model. So they have a somewhat simple structure. They're completely static, so they don't really have dynamics. So it's really just it's a completely static excitation that you can just excite or not excite. So these shifts shifts away from the origin, and the shifts of these lines are from these static vortex excitations. But the main features here, the really dynamics comes from not the vortex excitation, but these fermions. And so, for example, these lines here, which is hard to see, but there's a line here and these lines here. These lines here, these continuum line features, are basically because you have a continuum.
It's coming from the flip along the excited of the fermion. Is that what you're saying?
It's coming from the dynamics of the fermion. So basically, when you these pulses will excite fermions.
The fermions they look a little bit like bonds on a hexagonal lattice that have their own evolution. It's something like graphene.
Exactly. Yeah. They basically have the spirit of graphene. Exactly. Yeah. So basically, these line features here are related to they basically it's a continuum because you have a continuum of excitations basically of the entire band structure. Obviously the actual band structure of graphene has some sort of special structure, which is in momentum space. Here, because I don't have any momentum, I'm just looking at everything that's zero momentum. I don't necessarily see that kind of rich, structure, band structure in momentum space. And so here I see just the dynamics at the in the momentum space at the origin, basically. So I see the fermions and the kind of density of states. But the fluxes in this particular simple limit, they basically don't really have dynamics. So kind of just that, they're just kind of static things that I accept. And these lines are again because of the fermions. And it's not possible to see, but if you zoomed in and did a log plot, there's some fine features to this to do with actually how if you create a flux, how the fermions localize around those fluxes. So there's a little bit of fine detail, and we have to zoom in kind of and do a log plot. It's hard to see on this. Because the when you create these fermions, they don't have free dynamics. You've also created some fluxes. So the dynamics in the back end of these fluxes creates a little bit of extra information. And so this is all gone in the classical picture. The classical picture is one of these.
There's no more questions. Thank you again.
I should also mention at the beginning, I joined UCD last year as a faculty there. So I'm in UCD, and so if you ever, want to get in touch with me or talk more, I'm nearby, so feel free anytime.
Thank you very much. crystals